So that course next semester will be, will address all these issues about how materials respond. And in particular, I hope it will include the nonlinear optical response. Everything that I talked about here is the linear response to an electric field. So, got index of refraction, information, oscillator model, done that. Done that. Okay. So now we're up to boundaries and waves. I think I'm now officially a whole class behind where I intended to be. Maybe a class and a half.
Don't we have buffer classes
Yes.
for just this reason?
Yeah, I might have actually consumed the buffer classes already. Yummy.
Tastes like chicken.
Okay. So now we've got response to materials. And we have a dielectric function. We know where it comes from. We have the imaginary part of the dielectric function and the real part of the dielectric function. And now we want to worry about waves incident on boundaries. We have a wave incident on a boundary, and this would be my incident wave vector, which I'll call K. Over here, I'm going to make life easy for myself, and I'm going to ignore the magnetic permeability. Because for most important optical materials, the magnetic permeability doesn't play a major role. In a minute, to make my arithmetic simpler, although I can leave it there. I was going to make the dielectric functions real, but I don't actually have to. Okay, so I've got my incident wave. I've got my reflected wave, which I'm going to denote with a double prime, the wave vector of the reflected wave. So that's not kappa, that's K, right? And then I have a transmitted wave with wave vector K. And actually, just to, let's say, complete things here, I have a mu1 and a mu2.
What kind of materials are these?
Right now, they are just homogeneous materials. You don't need to know anything else. Homogeneous on the scale of 1/10 of the wavelength of light. That means that we can properly average the responses of the atoms over several thousand atoms. So I could talk about macroscopic functions. All right, this, unfortunately, is the normal to my surface, which I'll label as n hat. And I would have my incident angle, which is usually measured with respect to the normal in optics, and my reflected angle, and my transmitted angle.
The angles are complex.
That might be everything that I need
And the angles are complex.
right now. What?
And the angles are complex.
And the angles can be complex. All right. Actually, what I'm going to do, I'll do this as though everything's real. And then it will turn out, I'll just say to you, because the logic is understandable, if everything's real, that if I actually use complex indices in here, instead of the real dielectric functions, or real index. Turns out everything, mathematically, everything is treated identically. It's just that you get weird things like complex angles. Right? But it works. All right. So my incident field looks like this. I need a polarization, so that's what I'm indicating the polarization with there. Okay. E to the I, k dot x minus omega t. I'll make it propagate in the plus x direction. And as a result then here, B is, yeah, I'll write it like this. Square root of mu epsilon k cross E. I've written this is enough. This is the relationship between B and E. For materials that are not conductors, that's sufficient. We're done. Okay, as far as relationship between B and E. I don't need to write E anymore. Well, I do. Okay, I'll write it down. And then the transmitted field, E. I had to be careful. Oh, yeah, I'll write this like this. All right. This doesn't necessarily point in the same direction as that one does. In fact, it doesn't. But E to the I k prime graph x minus omega t. And B will have the same relationship. I don't have to write that down. I'll just write k prime cross E prime. And so this is transmitted, and this is reflected. Yeah. All right, what I'm going to do for my own purposes here is set this plane to be equal to the z equals 0 plane. All right, so the propagation is in z, and I've actually already made a drawing here which implies something. And it implies that the incident and reflected waves and transmitted waves all fall in a plane. It's called plane of incidence. And so these two waves form a plane. The refracted wave will be, the transmitted wave will be in the same plane. All right? What do we know? From the wavelengths, the relationships and the definitions of the K, we know that the magnitude of K must be equal to the magnitude of K double prime because they're propagating in the same material. And K, the magnitude of K only depended upon the wavelength, the index of refraction. Actually, it depended upon the absorption coefficient as well. And so we'll just call that K, and that's omega over c square root of mu epsilon in top material, 1 1. That can be complex. But we're not going to treat it that way yet. I'll just take that to be. Epsilon 2. That's it. Okay. So now if we sort of look at this whole thing, and now what we need to do is apply boundary conditions to this. Boundary conditions that we know already. One of them is that D1 perpendicular to the surface minus D2 perpendicular to the surface is 4 pi sigma free. Okay? If this is just a dielectric or an uncharged material, there is no sigma free. So D1 equals D2 perpendicular to the surface. We know that E1 parallel to the surface minus E2 parallel to the surface is 0. It's Gauss's law. No, actually, that's in the static limit. That's Faraday's law. I might as well, as long as I'm at it, E1 perpendicular minus E2 perpendicular is 4 pi sigma total, bound charge and everything. This one's usually not so useful, to be honest. B1 perpendicular to the surface minus B2 perpendicular to the surface must be 0. And H1 parallel minus H2 parallel is equal to K free. I don't know whether there's a 4 pi there or not, so I'll label it with it. So those are our, and I have another one that I could write that includes the free and bound currents for B. So we have 4 boundary conditions, but 2 of them could be written in a slightly different form. Okay? All right. All those boundary conditions for all these waves have to be satisfied in the z equals 0 plane, everywhere in the plane. All right. What that demands, satisfying those boundary conditions with these waves, demands that k dot x at z equals 0 must be equal to k prime dot x at z equals 0 must be equal to k double prime dot x at z equals 0. All the phases are the same. It also demands that all 3 wave vectors must lie in a plane. And as a result, k sine theta incident equals k prime sine theta transmitted equals k double prime sine theta reflected. All right. These 2 k's are equal, so that says that sine theta incident is equal to sine theta reflected. Angle of incidence equals angle of reflection. We can also prove this, by the way, using Fermat's theorem. How many of you were you forced to do that in Honors Physics 2 or somewhere about
Optics.
Okay, how many did it in optics? How many did it in Physics 2? Well, if you took it with me in Physics 2, you did it with me. Anybody here take Physics 2 with Stoller? I'm just curious whether, did he do that? Fermat's theorem?
Yes.
Yeah.
Good, okay.
Yeah.
So, the rest of you, tough. And what else? There's one more thing that I need. Snell's law. Says that n1 sine theta 1 equals n2 sine theta 2. I explicitly didn't write it as incident and transmitted because all of you remember it in this form. n1 sine theta 1 equals n2 sine theta 2. All right. That, again, comes out of this condition that the phases all have to be the same for incident, reflected, and transmitted waves on the surface. Okay? Snell's law. for a brief period was known as Descartes' law, because Snell was scared to publish the material himself during his lifetime. People were being executed for thinking too much during this period of time. So he didn't want people to know that he was thinking about optics. So he sent everything that he knew to Descartes. And actually Descartes was also scared about publishing, but in the end he did. And he published this law as Descartes' law, where he also then used it in a beautiful way to establish why rainbows have the spectrum and the angles that they do. And then after Descartes died, many years after he died, they went through his records and discovered that Snell had been the one to tell him. So first the Germans and then everyone else changed the law back to Snell's law. Have I mentioned that usually when I'm standing here it's totally irrelevant to the course content? Okay. So now we have all the things that we know from standard optics. I actually wrote out the boundary conditions here in their glorious form with all the fields. And I'm debating with myself whether to actually write them down. I think
In 3 minutes?
not. That's how much time I've got?
5,
Oh.
yes.
Oh, all right. We're going to finish for today then. And next class, I'll talk about the consequences as far as the reflectivity of light from surfaces. In particular, the Fresnel equations and Fresnel equations.
Good.